regional directors from some of the regional centers. And then we have also sent that link to some of the groups in which the experts and faculty members from other universities are there. So I don't know all of them, but I know some of them who are regional directors or assistant regional directors in IGNO's regional centers. So wait for a while if you we can access this. Yeah, yeah. Those who come later, and the people can later on see it. Yes, yes, yes. I think Sanjay, shall we start?
Yes, please go ahead. Yes. Thank you. Thank you, Dr. Rajesh.
Thank you, Dr. Rajesh. Esteemed speaker for today's webinar, Sri Sanjay Upreti ji, Dr. O.P. Sharma, Director NCID, and other senior colleagues from NCID, my senior colleagues from schools, different organizations, regional centers of IGNOU, and all those who are participating through social media platforms. So first of all, let me compliment Dr. Rajesh, Senior Regional Director of IGNOU Regional Center Trivandrum, and his team for organizing this webinar under the Innovation Hub initiative of the Regional Center Trivandrum. I am very happy to see that the Regional Center Trivandrum actually has taken a very important initiative of creating an innovation hub in the Regional Center Trivandrum with the active involvement of ISRO. And this is quite an achievement, I will say that it is definitely a welcome initiative by any regional center, and I congratulate RC Trivandrum for this. Today's lecture is an initiative taken by this innovation hub at RC Trivandrum, and the theme which has been chosen for the today's webinar, it carries a lot of relevance for all of us. I am thankful to Sanjay Upreti ji for agreeing to deliver a lecture on emerging developments in the field of semiconductors and quantum computing, and the opportunities which are there for innovations and the startups in the country. So thank you very much, Sanjay ji, for agreeing to our request. And we all know how important the role which the semiconductors play in our lives. They are, in fact, the backbone of the electronic devices, whether they are smartphones, laptops, household appliances, or automobiles. So now almost everything revolves around these electronic gadgets. So without these chips, there would be almost no smartphones, no radios, TVs, laptops, computers, or even the advanced medical equipment. So that is a major area of concern for any country in the world. And India's own consumption of semiconductor now it is expected to cross $80 billion by 26 and $210 billion by 2030. So that speaks a lot about how important this sector is. The chip manufacturing companies are largely, concentrated in countries like Taiwan, Japan, Singapore, or China, and it has serious implications for our country, not only in terms of economic development but also in terms of the geopolitical environment which it actually creates. So that's why this particular topic, I think, carries a lot of relevance for us, and we must know about how it affects our lives. And India has now tremendous potential, I will say, to play a key player in the global semiconductor landscape. So if we can properly utilize this potential, then India can definitely emerge as a major power in this sector. And it's a good news for all of us that India already has a semiconductor mission in the country, which aim to establish a robust semiconductor ecosystem in the country. So I think there is already a lack of awareness about how important semiconductors are. So in that connection only, we invited people from diverse backgrounds in our university. Most of them are educational administrators, but at the same time, they are serious researchers and faculty members. So a diverse group, and I will request our honorable speaker to make it interesting for everybody. That Sanjay is very skilled in doing it, I know. And in today's talk, I am looking forward to a much enlightening discussion. Thank you very much, Dr. Sanjay ji, for agreeing to our request. And I now request M. Rajesh to please further start further proceedings.
अभी शुरू हो रहा है.
Thank you, Dr.
Rajesh,
Rajesh ji.
just very sorry for interruption. I think some of the participants they are facing problem to joining, so please ask somebody to permit them.
Thank you, Dr. Rajesh. Indeed, this lecture is very important in the context when our country is talking about the semiconductors. Government of India has recently set up this India Semiconductor Mission under the Digital India Corporation, and in that context, setting up of 3 units recently by the Honorable Prime Minister. And in that too, when Sanjay Upreti ji will be talking about the possibility of innovation in startup, then I think it will be good for our students also, because this will not be remained only up to the big labs and other things, like in other areas in defense and space also. A lot of startups and innovations are being carried out by the universities and institutions. So in that context, I think this today's talk will be very useful, and because we know the importance of semiconductors, how important they are in our day-to-day life, particularly those who are having a science background, they can understand, but those who are not having science background, they can see the electronic devices, mobiles, telephones, and televisions, computers all around them. I think with today's talk, they will be able to understand that how semiconductors are playing role in that context also. So they will be recognizing, appreciating the importance of semiconductors, and also why this semiconductor mission, India Semiconductor Mission, will be useful for our country. And if it is properly implemented, then how it will be helpful to all of us, all the faculty and the students, and particularly the youth of the country, who would like to take their make their career in this field, or may like to be do something, some further research, or some kind of things in this area. So I think it will be good to listen to Sanjay Upreti ji rather than we talking, because time is very less and it is good. So thank you very much, Dr. Rajesh, for organizing this program, and this innovation hub which you have set up at the RC Trivandrum will certainly be very helpful in kind of vibrancy, and bringing new people for the university and the university students, and learning more about the things which we will be finding useful for all of us. So I think it will be good. We should listen to Dr. Sanjay Upreti ji. Thank you very much for inviting me.
Thank you. Thank you, Dr. Rajesh, Dr. Pandey, Dr. Sharma. It's good to see everybody back again. It's been, I think, many months, maybe a year over. Uh, so before I start, a few things I want to, cover. One is just want to make sure that we can turn off the videos once the talk starts, so that there are no distractions. So we can mute other people. Uh, as Dr. Rajesh said, I've been working at IBM, but right now I am not representing IBM as such. I will be just discussing as a member of the community, which has learned something in the past 25 years in this field. And I think considering the the diversity of the people who are attending this class, this lecture, I have tried to make it not very technical, but at the same time, these are extremely technical fields. So you will have to excuse me if things go a little bit more technical, and at the end we will always have questions. So feel free to ask as many questions as you can later on. I will try my best to cover both the topics of semiconductor and quantum. In reality, each of them is a topic of its own discussion for hours and hours, if not more. So with that, let me get started. I'm going to share my screen. Just somebody can confirm that this is okay. Let me see. Where am I? Window. Hmm. Uh, how do I share this? Slideshow. Play from the start. Okay. So understanding. Can somebody see my presentation, or how do I get this?
No, sir, not visible.
Not yet. Okay, let me see Windows entire screen. Maybe if I start screen two. It doesn't allow me that. It says cannot. Yeah, there is a present button, the present now, but it says that it doesn't allow. Let me see a window. Meet and terminal. Okay, if you can, that will be even better. Let me do that. Yeah. So just give me a minute. Let me send this to you through. WhatsApp. Where is this? All right. So Rajesh, I can send it to you, right, directly on WhatsApp? Okay. It's okay. Yeah, it's coming up. Yeah. Yeah, it's almost there. Yeah. Okay. Okay. Yeah, I know. In the meantime, if I can just try it one more time just to see if I get Windows screen, Microsoft.com, screen, screen 2. Okay. No, I cannot
No,
see.
no, no.
Okay. It doesn't allow. I don't know why Google will not allow me to share. Let me try one more time from my end. And let me see window. Aha. Looks like it's coming up now.
So I had a small suggestion whether we can split the file and share it as two sequence. It's visible, sir.
It's coming now, yeah.
Yeah, that's good. Okay. So this is, yes, it's visible. Can you give me the control or? Okay, let me see. It is still, yeah, okay. Go back to the page one. Yes, there is one page before this. Okay, yeah, that's fine. So I think, yeah, we can get started here. So the topic of discussion is, semiconductors and quantum computers. Basically, as I mentioned earlier, these two are, very, very complex topics of discussion. And my goal is to combine all of them into, both of them into one, trying to link as to why did we need innovation in quantum era, in quantum computing, and what are the things that your current technology cannot handle, and you know, uh, and there is a reason why quantum computers are needed for certain class of problems. So, starting uh, with semiconductors, if you look around, it's there everywhere. It's so ubiquitous. There is no place, these days where you don't see semiconductors. You see it in computing, whether it's a data centers or supercomputers or even your laptop, whatever you do. Most of the people these days have some link or the other. Even your mobile phones, they do lots of computing of their own. So that's one area. Virtual reality is another one. Space technology, everywhere you go, you have microprocessors, chips there. You have microcontrollers there. They communicate with people on the ground. You have storage systems, communication systems, just like your mobile phones. You have transportations everywhere. This automatic, cars, something like Tesla and others. In healthcare industry, where the technology is used these days in pretty advanced manner. Defense systems, of course, nothing can work without your extremely fast computing. Energy sector also, whether it's just the solar panels or windmills, anywhere you go, you have semiconductors at the heart of them. Not to mention the AI, and and because of that, when I say semiconductor, we really mean computing in general, which are basically chips, and they are all made up of semiconductors. So semiconductor becomes at the heart of all of these. Let's go to the next page. And this is where we can get started as to what exactly is a semiconductor and how did this all come about. So what is special? Now, the magical element in the periodic table is silicon. We all know sand. It's everywhere. You go to the ocean. Anybody who lives on the coastal area knows sand is everywhere. Not just the coastal area of the oceans, but also near the riverbeds. Sand is present everywhere. And the beauty of the planet Earth is the Earth's crust is full of sand everywhere. The main element here is silicon. The silicon dioxide is what sand contains for most part. And silicon has a very special properties that in a pure form, silicon is an insulator. Now, there are three types of materials that we come across. One is a insulator. We all know plastic, for example. It covers your live wire inside your home so that you don't get current, and that's insulator. Plastic is the insulator. The wire inside, which is made up of copper, is a conductor. A semiconductor is something which is in between the two. A semiconductor is something where at your will you can make it a conductor or you can make it an insulator, meaning it may or may not be able to pass current. And that's the beauty of these semiconductors, that these devices can be controlled by applying a voltage, whether or not a current can flow through these devices or not. So silicon is the one in the purest form. It's an insulator. When you insert some kind of let's say phosphorus, which is right next to silicon in the periodic table, if you add phosphorus to silicon a little bit, it can become a conductor. It has more extra electrons that can conduct, and electricity can flow through that. We call it an N conductor. If you dope it with boron, then you have a p conductor, where you have one less electron to flow and effectively one extra positive charge that floats around. So let's go to the next page. So from the silicon, this silicon to this doped silicon, where we make it conductor, we come to transistor. Now, transistors are the heart of all the chips that you see in the world, everywhere. So what's a transistor? Transistor again starts with a silicon. So it has a silicon at the bottom, this gray box that you see on the left where it's written NMOS. That's a silicon at the bottom, and the two green areas are those where you have N conducting region. So you have phosphorus doped in that region, and those two green areas. And in the middle you see the G written there. We call it the gate area. That's the polysilicon. So that polysilicon is another conducting layer on the top. And between G and the gray in the bottom, you have a very thin layer of insulator, so that the G does not short the bottom silicon layer. And this whole structure of three different types of materials, you have the N there, you have the G, you have S, G, and D. It forms a transistor. Now, what's a transistor? It's more like a switch. If you see on the rightmost part here, if you apply a positive voltage, for example, in this case, the current can flow from the N plus between the two ends, for example, in this case. Okay, and if you don't apply the voltage, there is no current flowing between the two ends. So that way, this thing acts, this gate acts as a switch. It's like you can turn on and off the current. Now, this is a very simplified version. We call it a planar transistor because it's pretty much like a flat surface where this structure is made. And this is the way the technology used to be until, let's say, late 90s. Okay, for first 35, 40 years of semiconductor and transistor invention, this was the technology that was used basically. Okay, we call them planar transistors. Now, this in a modern chip these days, the size of this is extremely small. Now, here it looks pretty big to you, but in general, a chip size in your mobile phone, for example, is, let's say, 1 centimeter by 1 centimeter. Inside that 1 centimeter by 1 centimeter, you have about a few billion transistors, few billion of these. 1 billion is 1,000 crore, right? So you have really a lot of them, and you have many more of those, many thousands of crores of transistors inside a small chip of the size of 1 centimeter by 1 centimeter, for example. So this is the transistor becomes the main driving force of everything that we do, all your computation, all your visual display, anything that you can think of. So let's move to the next page here. And I don't know if you can see this. Can you click on the center one? There is a video here. I think it. Okay. Well, anyway, I'll publish it
That
on
is in
the.
the PDF.
Yeah, I'll publish it on the on the Google Drive, so you can always look at it later on. But essentially, you start from the sand, from silicon on the left hand, silicon dioxide, and then you have this manufacturing process, and then you get a finished wafer. Wafer is the actual uh, manufactured chip. Now, this wafer has like hundreds of chips inside. It is it has each of those chip is like it could be a microprocessor, it could be any other kind of chip, and each of those chip has tens of billions of transistors inside them. So to go from here to there, I wish I could show you this video, is an extremely complex process. Let me see if I can play this video on my Google Drive. Just give me a minute. I think I may have the ability to do that. Let's see until. Okay, so I'm going to share this screen probably. Let's see if this will work. Just give me a minute. Dr. Rajesh, share now. Okay, it doesn't look like it's going to allow me to share this. Yeah, I don't think it allows me to share that, but that's okay. We can look at that later on. I'll publish this, on the Google Drive. People can always look at this later on. So let's move to the next slide, please. This is where the semiconductor technology is taking us today. So back in the 1980s, we used to have the size of the transistor about 3 micron. That was pretty small, considering we are talking about the mid to late 80s, and that's about the time when I finished my master's degree. We were 3 micron size, the transistor. The gate that I showed you earlier, that was the size of the transistor. Now, when I joined IBM in New York in 1996, we were working on 0.18 micron size of the transistor. And as you go down, go up in the years, since then until now, you can see that the size of this transistor has shrunk. And the more it shrinks, the more complex the technology becomes. So obviously, you can then have more number of transistors in the same size of the chip. So from 0.18 micron to 0.13 micron, 90 nanometer, 65 nanometer, all the way down to today, we are at about 3 nanometer. For those of you who are not science graduates or who don't understand this terminology, 3 nanometer is about 30 atoms of hydrogen, for example, lined up next to each other. So that's how small the size of these devices are. Now, these days, even though in the beginning, the size used to mention the transistor size, but these days when they talk about 7 nanometer, 5 nanometer, 3 nanometer, it is not necessarily the size of the gate length as such, but it is the feature size they call it. The smallest feature they can build with the present technology. Now, these are the cutting edge technologies. In fact, as far as the world is concerned, there are very few companies in the world which have this technology. And the 3 nanometer technology is only available to, I think, primarily 2 companies. One is Taiwan Semiconductor, which is the world leader in semiconductor, and then the Samsung Electronics. Samsung is another one that manufactures these. So they are the main one. Other companies like Intel and all, they are also working on their own. They are at, I think, a 7 nanometer or 5 nanometer maybe, but they still have to build a fab where these things can be manufactured. But in terms of manufacturability, Taiwan Semiconductor and Samsung Semiconductor are the only two that can do this at the commercial scale. Now, as the first slide that I showed you, where we had the transistor, that transistor is now different today. In the latest technology, we have what is called a GAA. It's called gate all around. So what was as a plane? It's called the planar transistor earlier. Now you see it's like can you go back to the previous slide, please? Yeah, let's just stay here. So we have Intel has what is called a ribbon FET, and Samsung has what's called MBC FET. It's a multi-bridge channel field effect transistors. FET stands for transistors, essentially field effect transistors. And ribbon FET is by Intel. They are pretty much the same technology. The one you see gray in the center is an electron micrograph of this technology. It's by IBM in the center. Intel also came up with this new technology called a Power Via on the right side, which has its own advantages in technology sector. But essentially, all of these are now working at nanometer scale. Okay, these are the devices that get built at the nanometer scale. Now you can imagine the manufacturing process that is required to build these, and it's an extremely complex system. If we go to the next page, I can show you what are the companies that are mastering in this. So we have Taiwan Semiconductor that holds about 54% of world market on this. And then you have Samsung Electronics of South Korea, which has 17% of market, it's basically second in the world. And then Global Foundries of the United States, 7%, and the UMC of Taiwan, again, 7%. So Taiwan as a country alone has about 61% of the world market in this technology. And 17% is Samsung, then 7% is a Global Foundries in the United States. Now there are other players like Intel has its own fabs, but over the last few decades, most of these fabs were shipped back to Taiwan or South Korea because most of the companies in the semiconductor companies in the world, they went fabless. And fabless means they were designing all of these in their companies, but they will not be manufacturing it. They sent for manufacturing, they sent it to one of these two companies, either Taiwan Semiconductor or Samsung Semiconductor. Global Foundries does not have capability to do the latest 3 nanometer technology. This will change in the next few years, in the next 3 to 4 to 5 years. This will change into US again taking over, because US is spending, as I mentioned in the beginning before the talk started, is US has promised to spend $250 billion of money into bringing these latest technology chips back in the United States mainland. That happened primarily after the COVID. We realized that there's just such a shortage of chips worldwide, supply chain disruptions and all that caused that. So most countries decided that, okay, because we depend on these things so much these days, that we need to have these things being built in our own countries. European Union also has spent, they announced their own amount of money to invest into these fabs. At the heart of all of these is the ASML. The ASML is Advanced Semiconductor Materials Lithography. This is a Dutch company, and you will be surprised. Very few people know this. You will be surprised that this is the only company in the world that actually builds the machine which is used in manufacturing all of these semiconductors. So Taiwan Semiconductor or Samsung Electronics or Global Foundries or any other company in the world that wants to make advanced chips, they need to get the machine from ASML. That's the only country in the world that makes this. So why that is the case, why nobody else can make it? It is an extremely, extremely complex technology. and nobody has been able to do anything like this. And this is the reason why they all have to depend on ASML to build these advanced manufacturing. So this is something to remember. Now, this when I'm talking about advanced manufacturing, I'm really talking about 3 nanometer, 5 nanometer, maybe in the future, in the next few years, 2 nanometer and down to maybe 1 nanometer technology. But you don't have to build just those. 95% of the world requirement, things that we use in general, don't need this like this most advanced technology. They can work with the 22 nanometer, 14 nanometer, even 7 nanometer technology. So when India announced all of these, when a country starts manufacturing, they don't work on these advanced technology. It is next to impossible to do that. You have to be able to build just the previous, just the earlier, which is called mature technology, and work with that. That meets most of your requirements. Advanced technologies are only used in areas, say, like, compute in let's say some research areas or maybe defense areas and others. And for that, you need to have that technology available in this. And I think, as far as India is concerned, we are still much farther away from there. But to do that, you should be able to build the infrastructure, build the ecosystem, build the supply chain. And to building the supply chain, you will need these these mature technology first. So once you have the mature technology working in your country, you have the whole supply chain working in the country, you have the whole system working, you have the expertise of the people, you have the labor force to meet all those demands. Then you can start working on this more advanced technology nodes. And then, because then you will know how to do that, and maybe other companies can come and invest in there. So now this one, the world's fastest supercomputer. So where are those chips used? They are used in, as I said, everywhere, but computer is the main place where they started getting used, and even today they are the main place where they really get used. Now, today's world's fastest supercomputer is Frontier. It is both of the world's number 1 and 2. They're both in the United States in different labs. On the left, you have is in the Oak Ridge National Lab, which in the United States. On the right side, you have the Argonne National Lab. So Oak Ridge National Lab contains the world's fastest number 1 Frontier supercomputer. It has a computing power of 1 exaflops, and 1 exaflop, as you can see, is 18 zeros after 1. Okay, it's 10 to the power 18 uh, uh, calculations every second. That's how fast this computer is. So it can do in 1 second what the world's entire population, if let's say every human being on this planet, we have about 8 billion to 9 billion people right now in this planet, if everybody in this planet did 1 calculations 1 second, it will take us 4 years to do what this machine can do in 1 second. Okay, so for 8 billion people in 4 years, every second we are doing a calculation continuously for 4 years. That's how much it can do in 1 second. So these machines are extremely fast, extremely powerful machines. They are used for everything from defense research to searching for new materials, to studying new molecules, to build better medicines. It's used everywhere, and nuclear research, physics, other part of the physics, space research. It's used in all of these. As you can see here, this Argonne, the Frontier machine, for example, has almost 9 million CPUs and GPU cores combined, on this supercomputer. It also has over 700 petabytes of memory total, which is, and as you all know, a petabyte is 1,000 terabytes, right? So 1,000 and a terabyte is 1,000 gigabyte. And so 1,000 gigabyte is 1 petabyte, and 700 of those. That's how much memory these machines have. So it's practically unlimited. You might think that who really needs that much computing power? Well, when you start working on problems like nuclear reactions or molecular studies or discovering new drugs, you will realize the amount of computing power you need. and that's where these machines are used. Aurora is another one. It's pretty much the same. Number one or number two, they have similar power that is used at Argonne National Lab. Again, the similar stuff they do: advanced research, defense research, national security research, and all that stuff. So let's go to the next page. Can you move to the next page, please? Thank you. No, go back. Yeah. I think you might have to go back one more page. Wait, there is. Yeah. Okay. So that's right. So no, right after that. Yeah. So let's look at the classical modern computer. Yes, this one. So what does the modern computer do? So these computers these days, we talked about transistors, we talked about where they're getting used, all these supercomputers everywhere. So what does a computer normally do? A computer has bits, right, zeros and ones, and these bits are used to build transistors. Sorry, these transistors, are used to create these bits, and together these transistors they build what is called gates. And we have these shapes here. You see an AND gate, an OR gate. Those of you who are who understand electrical engineering a little bit, or who have done physics, you will understand some of these gates. So these gates are logical devices. They do computations for you. You send bits at the input, and bits on the other output, they come out. You can do multiplication, you can do addition, subtraction, division. That's pretty much everything all the computation is. So everything that you see, whether you are watching a movie, or you are typing something, or you are launching a rocket or somewhere, at the heart of all of that is really just some addition and some subtractions and some multiplications and some divisions. That's it. That's really everything that you have at the ground, and all of that is being done by the zeros and ones, the bits of a computer, and that's done by the transistor. So it uses Boolean algebra. Boolean algebra is the mathematics branch that deals with these kind of logic, ones and zeros. Now, one thing about the classical computer is it's fully deterministic, meaning if you give a certain number of input to the computer, you are guaranteed to get the same output every time. So it's not like when you give some input today and now, and you're getting some output. The next time you give the same input, you're getting a different output. That means your computer is not working. Okay, something is wrong here. So we call it deterministic because the idea is that if you repeat, and that's a good thing to know, because if you have a calculator, for example, if you say 2 plus 2, you should get 4. You shouldn't get 4.5. You shouldn't get 4.2 or 3.9. You should always get 4, guaranteed. And that's what the modern computers do. Well, but at the same time, another advantage of these computers is they are extremely fast. So today we have about 5 gigahertz speed of these computing processes. Okay, we don't have computers faster than 5 gigahertz, but we have more cores in computers. So these days you have the 3-core, 4-core, 5-core, whatever, 4 cores or 2 cores or 8-core processors. So these multi-core processors, essentially what they do is they are trying to compensate for the performance, because we cannot increase the clock frequency, we cannot increase the frequency of this, we cannot increase the speed of these processors. And why can't we increase the speed of these processors? Because it gets hot. Your chip actually gets very hot. You will be surprised that this tiny chip is there. It can consume almost 100 watts of power, even more power if you are using a graphics processor like a GPU or something like that for games. And some of these big graphic processors, they can even consume kilowatts of power. So again, lots of power gets used, and that's because of the frequency. So what the engineers decided is that maybe we should just increase the number of cores. So each core can only run at 5 gigahertz or whatever. So it's a small, but you have multiple cores, so something like a parallel processing you can think of. Now, it's also sequential data processing, meaning, you instruction by instruction, you send it to computer, it does something and comes out some other, some results. And it's all defined by classical physics. Everything that you learn in your, BSc, MSc course, that's really all you need to understand how a computer really works. So let's move on to the next page, please. So what are the limitations of the classical digital computer? I'll call it classical for a reason, because we are moving on to quantum later on. So the limitations are that you can, you can build more powerful computer. I just showed you a supercomputer there, right? It can do so many calculations, 10 to the power 18 computations per second. That's a lot of computations. Okay, you can build a lot of those, but there are certain types of problems in nature and in the world, even in human created problems, which which are exponential in nature. Meaning, if you increase the number of parameters, the problem size can become exponentially larger. And exponentially larger means instead of doubling it, let's say you double the size of the input, then the problem becomes double. No, problem can become 4 times. If you triple the size of input, problem can become 8 times. So things can actually go much faster than uh, uh, the number of parameters you have. For example, if you have two people, there are how many ways you can connect them? Just one way, connect two people, A to B. If you have three people, how many ways you can connect them? A to B, A to C, and B to C. There are 3 ways now, right? Well, what if we have 10 people? Now we are talking. Now we are actually increasing. The number can be much more. And if you have like 1,000 people, it can go into millions and billions probably, the number of connections you can make. So these are the class of problems which can grow exponentially. Prime factorization is one of the example. All of us use computers, all of us use mobile phones, we do banking through our phones. It has to be secure. The security of all our system is done using what is known as RSA encryption technology. RSA is the name of the 3 scientists who worked on that method a few decades ago. That is still being used. And the reason why that is such a secure way of doing all your transaction is because uh, it relies on what is known as a prime factorization. It's a large integer with hundreds of digits in it, and it is product of 2 prime numbers. And your goal is to figure out what are the 2 prime numbers. You cannot run a supercomputer to figure out that. Even supercomputer cannot really break that. So that's why it's pretty solid, encryption technology. So when people say, "Oh, somebody broke the encryption," or no, nobody can actually break. No human can break RSA encryption. The reason why people's security gets breached, whether it's companies or in institutions or governments, is because people are sloppy. They don't write good passwords. They don't follow the guidelines, and that's why the security gets breached. Not because anybody can break this encryption. Nobody can break this encryption. No technology today exists that can break these encryptions. Okay, so another thing is accurate molecular modeling. Molecular modeling is one of the parts that why is it needed? We want to discover new materials which are more strong, much lighter in weight. So today we know steel is a pretty strong material. But it's pretty heavy too. What if we can make materials, say something from plastic, but they are much stronger than steel? Won't that be better, right? So you are trying to figure out how can we design new materials. To do that, you need to understand how the molecules and atoms they behave, how they interact with other molecules and atoms. Those interactions require lots and lots of the chemical reactions and other physical physics studies. And you are talking about hundreds and thousands of electrons systems together, right? You have hundreds of electrons and thousands of electrons in many atoms combined together, their behavior. To do that, even a supercomputer cannot handle those kind of systems. So same for drug delivery. If you want to create a new class of drugs, which is more individualized medicine, then you will need again similar thing, genetic drugs which affect the genes, for example, right? Or gene studies. You want to figure out why does cancer happen. You have to study at that level. So all of these class of problems are something that your supercomputers, your classical supercomputer, they cannot really handle. Transistor size is getting small, right? I told you already we are at 3 nanometer, 5 nanometer. Pretty soon we are going to 2 nanometer in the next couple of years, and then maybe 1 nanometer. What after that? Below that, less than a nanometer, you are already in the quantum domain. Your quantum effects will start showing up. Your yield will become much less. You will not be able to produce good quality chips. They won't be able to function well, and you are stuck again. So we need innovation in this area too. So power dissipation keeps us from increasing clock frequency. Now you want to make a computer even faster. As I told you earlier, if you make it faster, it becomes more hot. If it becomes more hot, it will burn your chip. So you have to now put more cooling. That means that requires more energy, more power. And remember, you are not the only one. The whole world is doing this. In fact, the amount of energy used to cool these computing systems today are even used by these computing systems today. If you combine the whole world, it's about 20 to 30% of world's energy consumption that is used in all of these. Okay. Unfortunately, almost half of that goes into just cooling the system. So you are heating it up to do the computation, that you are cooling it down because it got hot. So it's a horrible way of doing things. So how about discovering something where it doesn't heat up? You have our new materials where you have much less heating effects, and you can design something better. So people are studying those as well. Let's go to the next page, please. So with all of that, with kind of problem that we have, Richard Feynman, a physicist, a Nobel Prize winner, in 1981, he had a vision. He knew computers are coming up. This again, remember, this is 1981. So he didn't have the computers like today we have, very powerful computers. But he knew computers are there. At that time also we had computers much more sober type in terms of their computing power. So what he said is that if you look at the nature does not work in a classical way. Our normal way of thinking, which is okay for playing football or sending things, rocket to the moon or other places. But if you look at, for example, how the plants work, how does life work? How do genes work? How does our whole atomic structure work? Based on which everything in all the material in the world, in the universe, is made. It's all quantum mechanical. So he says that if you want to solve problems related to all of that, you need to have a system which works in a quantum mechanical way, not in a classical way. Okay, so that was his idea. So he really, you can say in a way, he was the driving force to build what is today as quantum computers. Okay, let's go to the next page. So, what's a quantum computer? Now, the quantum computer is basically a different type. Remember, so far what we have talked about is a digital computer. Okay, a digital computer is also called a classical computer because it's built on the normal electronics that you study in the class in your classrooms, and it's a normal physics, what your day-to-day physics. Okay, simple rules. Discrete mathematics and all of that. That's what is used in the classical computer. The quantum computer does not use that kind of transistor. Okay, so it's a different type of computer. So what does this computer have? This computer is basically, you can think of it more like a mechanical machine as of today, right? It's a mechanical device with lots of pipes and other things going on. Resonators are there, and even in the future, you will not be having a quantum computer in your lap, like a laptop today or in a mobile phone. What you will do, and even now and in the future too, what you will do is you will be connected through cloud to one of these computing machines. You will still be using the classical computer, like a normal digital computer, your mobile phone or something which works on a chip, which works on semiconductor. But it will not be you will not be directly having a quantum computer in your laptop. Okay, at least not the technology that we have today. Now, maybe 100 years from now, people figured out how to maneuver all the atoms and molecules. Then maybe yes, but at least whatever scientists and engineers think today, that is not going to happen. One of the reason is this: the bottom of this chandelier that you see here on the left, top left, where it says IBM Q. At the bottom of that is where the chip is sitting. The chip, IBM quantum chip that you see at the bottom, it is cooled to practically 0 degree Kelvin. And if you don't know what that 0 degree Kelvin is, 0 degree Kelvin is the coolest place in this whole universe. Not just on the Earth, not just in our solar system, anywhere in the whole universe. You cannot have anything below 0 degree Kelvin anywhere. Okay, even that you cannot really build absolute 0 degree Kelvin. So what people do is, engineers, they can build like a millikelvin, so pretty close to 0 degree Kelvin, but millikelvin. Okay. Now, the idea is to be able to control and freeze, quote unquote, freeze some of these atoms and electrons in certain states, so then you can do computations with them. Otherwise, at anything larger than that, any temperature larger than that can cause this system to move around a whole lot. Remember, we are talking about atomic scale. We are talking about subatomic scale here, electron state scale. So they have to be very stable. So these quantum computers are designed with this cooling in mind. So it doesn't matter which company makes these quantum computers, cooling is one of the major part of all of that, especially if you are working with electrons, for example. Okay, because you don't want any interference. Anything little bit less than that, slightly hotter than that 0 degree Kelvin or millikelvin, and things will start becoming unstable. If you go to the next page, right, again, I don't think we can see the video, so we can move on from this page to the next page, please. So yeah, let's move to the, yeah, okay. So before I go here now, one thing to remember with these quantum computers is, as I said, it is a chip which is kept at extremely low temperature. The way this chip does computation is using quantum physics. Okay, and the quantum physics is a very different type of physics. Normally, in your real life, you kick a ball. What happens? So for example, you are playing a football, right? So you kick a ball and you pass it to somebody else. The somebody else knows where the ball is and can really reach there and get the ball, right? That's how normal behavior of classical physics is. Where in quantum physics, if you kick an electron, you really don't know where that electron went. And for that matter, you cannot even know where the electron is to kick it. The particles, they behave like they are everywhere. It's almost like gods. They are called God particles for a certain reason. So their behavior is very, very different. It is not at all obvious to human beings. Okay, so their behavior is very different. They behave in a very uncertain way. They have a duality. Like sometimes they behave like particles. Sometimes they look like waves. We don't know which one it is. Sometimes and their entire behavior is probabilistic. The classical computer, remember I told you it's deterministic, meaning the same input gives you same output. If you use a quantum computer, the same input may not give you the same output, but it's a probabilistic. It will give you an output with a probability. It will tell you the chance of this result is much higher than chance of some other results, but it will still give you a chance for that matter. Okay, and your goal is to improve the chance. If your chance is 99%, you are in pretty good shape. If your chance is 50-50, you don't know what the right result is. Classical computer will never have 50-50. It will always have a definite answer for any problem that you give it. But classical computers cannot solve all kinds of problems. And in nature, everything is quantum mechanical. So you need to worry about that. They also have this effect of superposition. So here is this picture of the cat. If a cat was inside a box, and if I asked you whether the cat is dead or alive, there's no way you can tell, right? Some people might say it's dead. Some people might say it's alive. If you don't know it's moving or not, but there is no way to tell. So as far as a physicist is concerned, as far as scientists is concerned, they will say, well, the cat is in the state of alive and dead both. The only way to find out is open the box and see whether the cat is alive or dead. But once you open the box, you have disturbed the system. This behavior is pretty simple to understand at atomic scale. Let's say you want to see an electron. How will you see an electron? How do you see certain things? You see something because the light falls on it and it comes to your eyes, and then you can see it. You are seeing me because light is falling on me. It's going through the computers, and you can see in your screen. Well, if the light falls on an electron, light has energy. The electron will get kicked out. It will be somewhere else. And if it comes after it kicking it out, if it comes back to you, what you see is not where the electron is. It already got kicked out. Light doesn't kick me out, but it kicks out the electron. So the problem is, if you at atomic scale, there is no way for you to find out what the system is without interacting with the system. And the problem of interaction is you're disturbing the system. So this is one of the biggest issues in quantum physics. That how do you measure something without disturbing it, and that is not possible. So this is the behavior in the quantum physics. I don't want to go into too much of detail. It's a very different science, but the idea is that they have these properties called entanglement, interference, superposition. Entanglement means the particles can entangle with each other. That means they behave as if they are like twins. They are like they are connected to each other, even though they're nothing connecting them. You can have an electron in America here, another electron in India. They are both entangled. And if I do something to the electron here in America, suddenly the behavior of the electron in India can change. And that has been observed. People have sent entangled particles to space, and they have seen their behavior change when you do something on the ground. And so this is like Einstein was baffled with this. And he even said that this is crazy. How can how can system respond to something which is so far away, because the speed of light is finite. Nothing travels at infinity speed. So all of this behavior is part of what a quantum world is. So let's move on to the next page, please. So this is how a quantum computer starts getting built. So first thing is, remember in the classical world, you had something called bits, zeros and ones. In a quantum world, we have something called qubit. A qubit is something like a bit, but it has a different property. It is not in a specific fixed state. A bit, remember, is either 0 or 1. A qubit can be in both the states of the same. It can be 0 and 1, or it can be anywhere in between. It can be like 30% 0, 20% or 70% 1, or 40% 1 and 60% 0, things like that. So how are those qubits made? So this is one of the technologies. There are a few technologies I have outlined here: trapped ions, neutral atoms, and all of that. I'm not going to go into that. At IBM, we use superconducting circuit qubits using niobium and aluminum and on silicon wafers. And it builds what is called a Josephson junction at the end, where there's a quantum tunneling effect that happens, and that's how these qubits are formed. I will skip this slide to go to the next page because this is too much of technical detail. Let's go into this. So this is the general behavior of a qubit. As I told you earlier, a bit has zeros and one very separate. You can distinguish them. A qubit is, as you can see, it's like a gray area, like it's a single state. So you don't know where your qubit is. Is it in state 0 or is it state 1? It could be in a mixed state. It can be a combination of zeros and ones. If you have two qubit system, it can be in a superposition state. It can be in a state like as it shows here on the second side here, both of them being in 0 0. One of them is 0, another 1, another is 1 0 and 1 1 state. And any linear combination of them, these alpha, beta, gamma, delta, those coefficients here, they are like, it can be in any state. So it can be 30%, like a 10% in 0 0 state, 20% in 0 1 state, some percent on 1 0 state, and some percent in 1 1 state. And so as you can imagine, like there are practically infinite probability, different possibilities here. And this is the beauty of a quantum computing. The advantage of a quantum computer is, unlike in classical computer where you are in fixed state, a quantum computer can be in multiple states at the same time. So if there is a way, if there is a mechanism in which you can convert this into a computation, like computing, you can do like a practically large number of calculations simultaneously, because a system can exist in all those things together instead of being only in one state. Okay, at one at a time. Remember, we talked about sequential computing, right? You did one computing, then you do next computing. Here it can do all of them together. So today's quantum computers, what they are is they're not as fast as 5 gigahertz that we have in the modern computer, but the quantum computer can do like a billion things together. So it's like 1 billion people doing computations together instead of one person doing at a time. So even if one person is very fast, but 1 billion people doing the same thing together, even if they are half as slow, will be much more powerful thing to do. And that's where lies the beauty of quantum computing, that a quantum computer can do things in parallel. And that's why it is the perfect type of computers which are designed to solve those class of problems where a classical computer like a supercomputer also cannot handle. Now, let's go to the next page. It has its own limitations. So quantum computing has what is called a quantum noise. And quantum noise, there are some sources. It has a decoherence time. The decoherence is something interesting. What is a decoherence? A decoherence in a quantum computer is for how long can you keep these group of electrons, which are your qubits, for example, in a given state. Okay, remember I told you they are at very close to 0 degree Kelvin, but they are not exactly 0 degree Kelvin. So what happens if there is a fluctuation there? Something goes on. So today, the most advanced technology in quantum computing has the decoherence time, means the time for which the system remains stable about zero point 0.1 millisecond, 1/10,000 of a second. So that means it cannot even last for a millisecond, forget about a second. And you have to do all your computation in that zero point 0.1 millisecond time. That's too bad, right? That's why we are still in a very early stage, very infant stage of a quantum computing world. We really need computers which can be, I mean, your normal computer can last for hours and days. You can keep it on. I have my laptop on for last 4 or 5 months. Nothing happens to it. Your quantum computer will not last a second. It will reset itself. So you have to do all your calculations in a much shorter period of time. So you are trying to build a machine where this decoherence time, the time in which the things become just completely useless, is much longer, so that you can remain coherent for a longer amount of time, and you can do much more computation. There are other sources of errors. There are quantum errors here. Interaction with the environment, electromagnetic waves, anything. So you have to shield this whole thing because remember, we are working at the atomic and electronic scale. At that scale, it interacts with light, it interacts with all kinds of electromagnetic waves, magnetic field, electric field, any other field. So you have to really separate it from all of those kind of disturbances. And that's where that technology is. That's where people need to start working on. People need to start thinking, okay, how can you build machines where none of these things will be where we can reduce the quantum error, we can reduce the quantum noise. And that is a game that is going on in the industry today. Which company comes up with a much lesser quantum noise and much lesser quantum error? So let's go to the next page. And I'll show you this picture here. This picture shows you what is known as quantum volume. So on the, if you go from the bottom to the right, that's the number of qubits. The number, as you increase the number of qubits, the computing power of a quantum computer will increase. But it doesn't increase a whole lot, because if you have a lot of error, quantum error or quantum noise, right? So on the, if you go from the bottom to the left top, you see the error is decreasing. So your goal in quantum computing is to reduce the error, the quantum error rate, and increase the number of qubits. It's much harder to keep, think of a classroom, right? Most of us are teachers here, right? We know how the classroom works. If it's one student, it's very easy to control that student. Imagine if there are 100 students in the class. It's very hard to manage all of them, because they will be talking to each other, disturbing. That literally happens with the quantum system too. If it's just one electron, you may be able to keep it stable for even many seconds. But when you are talking about many electron systems, say 100 electron system or 200 electron system or many other qubit system, keeping them in stable configuration to you do your calculation is an extremely hard task. And we have come to a stage where people have started thinking as to how to do that work. And remember, nature is already doing quantum computing. Look at the trees, look at all the life forms that get formed. That's all happening at the atomic scale, at electronic scale. That seems to be working just fine. So we have a scope here. We need to figure out how does nature work at that level, and how does it figure out how to build structures, rise from this building life forms. Okay, and so this is one area where lots of innovation, of course, is needed. Let's go back to the next page. So far I've described to you, just a rough idea on the top as to what a quantum computer does, how it is built. It has its own, and what benefits you can have if you can have a really perfect quantum computer. But a perfect quantum computer also has security implications. As I told you earlier, the RSA encryption that is used by all your banking, your defense system, everything security, right? All your emails are secured. Emails are always sent encrypted. OTP, all the password that you use, everything that you use, they are all sent through secure channels. Well, what if you have a perfect quantum computer? A quantum computer can break all of that. Let's go to the next page. Here. So, Peter Shor is a pioneer in this field of quantum computing, right? In the cryptography field, he came up with this an algorithm. It's called Shor's algorithm, and I'll talk about that a little bit later here. But before that, let me finish this page. If today what we are using, RSA 256 or RSA 512, that's pretty much most of the banking industries, most of the technology, or even defense and everywhere, we use that kind of encryption to secure our information. A supercomputer today will take about trillions of years to decode that. So we are perfectly safe, right? We don't have to worry about, nobody can decode it. No countries, no person can do that. Now, obviously, individuals don't have that much power, but not even a country has that much power today. But what if you get a perfect quantum computer, and we have, let's say, 6,000 qubit quantum computer with a very low error rate, practically, no error rate. That 6,000 qubit computer can decode this whole RSA to 2048 in about seconds of time. Okay, so now it's scary, because if a country, for example, can build a quantum computer which can break security codes, then all your communication, all your transactions, whether it's a defense communication, satellite communication, your banking transactions, your email, your privacy, and all of that, that's all broken, right? So they can see everything they need to see. And that is a problem with these quantum computers. But with the problem comes a challenge. You need to find out, how do you make something quantum safe, right? And I'll talk about that a little bit. So remember, today we are not there. Our decoherence time, the most advanced technology as of today. The Google's quantum computer had, as of 2019, we had about 50 microsecond decoherence time for them. That means it can only stay stable for 50 microseconds. IBM's is 100 microsecond, 0.1 millisecond, I told you earlier. And it doesn't change a whole lot. There are some systems people have claimed that maybe a few electron system they have been able to keep them stable for maybe a second or maybe a few milliseconds or so. But that's it. You don't have a large number of qubit system stable for more than few milliseconds or so. It's not, at least it's not known anywhere in the world as of today. Let's go to the next page. So what Peter Shor said is that how do you break this whole technique is essentially, as this picture shows here in the Shor's algorithm, a classical computer will take about 28 trillion years, right? I just showed you earlier, right? A 2048 RSA encryption. A quantum computer can finish that in 100 seconds if you have a perfectly built 6,000 qubit quantum computer, for example. The idea in Peter Shor's algorithm was that an exponential problem needs to be dealt with in an exponential domain. If a problem is exponentially increasing, you need to have a technique which is also exponential in nature. So together they can solve the problem. You cannot have a linear technique to solve an exponential problem. That's the bottom line of all of these. So he has devised an algorithm which does this whole thing using quantum computers. Let's go to the next page. So let's go to one. Can you skip this page? I'll come to this later on. Let's go to the last page here. So this is one of the areas we worked on as to how to prevent quantum computers from, decrypting a security system. So we published this work, in 2020, and we were working on it back in 2018 or 17 time. The idea here is that this technique can do secure communication without an effect from quantum computers. Quantum computers will not be able to break this kind of encryption technique. Okay, so those of you who are interested, you can always go on Google patents and search for this, and then you can look it up as to what this technique does. So we tried to be upfront about it, because quantum encryption is quantum decryption is coming in the next decade or so, maybe. So when that happens, you should be ready. So this is one of the techniques that we have. So let's go back to the previous to this page again. And these are the opportunities where we want people to start thinking about. So we went over semiconductor technology, we went over quantum computers here. The biggest challenges in semiconductor technology today is supply chain streamlining is uh, is is an issue. Remember what happened during COVID, right? So if you want to build something somewhere, let's say you have semiconductor manufacturing happening somewhere in India, say in Gujarat or in Assam. How do you ensure that in case of a national emergency, the supply chain is not disrupted? Should things be available locally? Should there be multiple avenues for supply chain? Now, a supply for a semiconductor company is in many folds. It requires all kinds of materials, all kinds of vendors to provide different setups. You can go to any of these, say, go to TSMC or even Intel's website. They can tell you the entire supply chain they use, and you can figure out that how to build that. So you need to have a setup available that with India's population, India's young population, enthusiastic people, we should be able to have very solid, very robust supply chain available in every region, so that you are always ready. Use of AI into manufacturing process is something which is happening these days. It's a slower, but hopefully when this new facilities get built there, that is one area where this will be AI will be used. So people should start thinking about that as well. We need new techniques to automate building devices at sub-nanometer scale. Right now, of course, we have, of course, the humans don't build them. Machines do build these devices, like photolithography and other techniques. But uh, when you go to sub-nanometer, like 1 nanometer and below, you are now looking at even in new science. We don't even know what to do there. I mean, right now we are stuck. We are really hitting a wall here again. That we don't know what is the future of semiconductor beyond, say, 1 nanometer. Okay, we have exhausted all the techniques we have. The latest we have is gate all around. I just showed you earlier, and those 3D transistors. And beyond that, nobody knows where things are headed. So that's one area people should start thinking about. What kind of devices can be built as transistors? And different people have different thoughts on those, but that's one area people should be doing research in. New materials to reduce the power consumption. As I told you earlier, power is one of the biggest factor why the technology stays at one place. Like we have not been able to increase the frequency of operation. It's not like we cannot increase the frequency. We have techniques to increase frequency. We can go to terahertz if you want to. Problem is, if you go into terahertz, your chip will melt in milliseconds. Okay, so it's just not possible to do have. You can't even have devices switching that fast. So you need to come up now with a completely different way of manufacturing things. Maybe build a completely different type of manufacturing, not just semiconductor, but somewhere in between semiconductor with photonics and with something else that can give you all of that benefits without the problems of those technologies. So the power is one sector area which is semiconductor technology is always looking for new areas. In fact, all the advancement that have happened have really addressed the power factor in semiconductor. From planar transistors to 3D FinFETs to now the gate all around, the whole idea was that how to reduce the power consumption and how to improve the transistor size as well as efficiency of the devices. On the quantum end, uh, as I mentioned earlier, decoherence time scale is the biggest issue right now. We are at just one thousandth of a second, actually 1/10,000th of a second. We would like these computers to this system to be stable for hours and days instead of milliseconds and seconds at the most. Error correction is another issue there. Whatever we have today, there are lots of errors, quantum errors that happen, and that basically prevents these machines to be very powerful as much as we want. The general trend is that we expect these things to be available in about a decade or so. So we still have time. India can start, people can start working on this, and don't just repeat what other people are doing. Think something new. Come up with your own ideas. First, read the basic physics behind all of these. That's the first thing you should know. I would like every institution to have people going through these classes in quantum physics. Basic quantum physics doesn't need a very sophisticated quantum field theory or anything like that. This quantum physics is good enough to understand the basics of all of that, and then go into invention mode, trying to figure out, okay, how do I come up with a device which will do much better, which will have less of these problems that we are talking about. So again, instead of absolute zero temperature, how about a room temperature quantum computer? Can you build that? The nature doesn't work at the room temperature. I mean, all your plants and everything are happening at the room temperature, right? So it's nature doesn't need absolute 0 degree cold temperature. So we need to come up with something new. Think outside the box. Think what else can people do? What else can we do? And at a scale. Because remember, ultimately you have to convert that into a computing machine. And of course, as I said, we need to have workforce training expertise. Unfortunately, most of the schools and colleges are still teaching things which are about 5 or 10 years behind. And this technology is really the most advanced technology we have. Your entire generative AI, for example, it uses the whole semiconductor technology as of today, but in the future it's going to use quantum computing, because generative AI requires these foundation models. The foundation models are or the large language models, which are part of the foundation models. They require months and months of training time, and they consume megawatts of power and enormous amount of computing resources only large companies can have. So we should really be thinking about how do we make sure that we use quantum computers for the generative AI techniques. And to do that, we should have quantum computers which are stable enough to do all of that stuff. So the future is going to be quantum computers using the AI work instead of the digital computers. But at the same time, you will need digital computers to be able to interact with quantum computers. So both of them will be there. But hopefully in the distant future, the quantum will take care of most of these parallel tasks, because the AI part is almost 100% parallelizable. That's why GPUs have become so important in this whole AI field, and that's why Nvidia company became the pretty much the number one company in the world in this field, because they are all using graphics processing units, and GPUs can do like 100,000 parallel computations at the same time. Quantum computers can do billions of those parallel computers. So that's where we are now. I think I'll stop here. It's time to take questions and maybe go through the other discussions.
Yeah.
Thank you.
Thank you very much, Sanjay ji. Yeah. Yes, yes. Yes, thank you very much. In fact, what I feel after listening to your lecture is that those countries which master this technology, the quantum computing, will definitely rule the world now in the coming
Absolutely.
100 years.
Absolutely.
One thing which comes to my mind is that as far as these semiconductor technologies are concerned, we have these quantum effects started becoming visible now, means at the scale we are working.
Not really, not up to 3 nanometer, 5 nanometer. I mean, if you go into very accurate details, maybe yes. But remember, the yield today in semiconductor technology, yield is a measure of how good quality chips you make. So let's say if you are making 100 chips, how many of them are good, meaning functional, right? And the yield today is, I think, about 20-30% at the most. That's where we are. In fact, about a decade back, it used to be 7 or 8%. People were happy with 7 or 8%. That means out of 100 chips they made, only 7 or 8 of them were good quality. So considering that, today we are doing better. But with that yield, it's not 100% or it's not 80-90%. Quantum effects really don't take that much front stage, but it's coming. We are already 2 nanometer. As I said, 2 nanometer is 20 hydrogen atoms combined together, right? Actually, silicon atoms are many few of them. Silicon is 1.5 nano angstrom. So we are looking at 15 silicon atoms maybe. So we are really coming very close to that, and that's where the new floodgates will open up. That it's such an exciting time for people who are in physics area, people who are in mathematics area, to see now whatever you learned in your BSc, even intermediate BSc, even MSc, all of that will get you. So I would say spend time, read it, and it's just a basic part of quantum physics. It's not even like you need to go into quantum field theory or some other complex part of quantum physics, but just a basic level.
Acha,
You will
Sanjay,
learn a lot.
we have with us actually a very senior our colleague Dr. C.K. Ghosh. He was director RSV long back,
Okay.
and he has raised his hand. So I want to take his question first,
Okay.
and after that I request Rajesh to please coordinate this question answer session.
Sure.
Thank you, Dr. Pandey, Dr. Rajesh, for this opportunity. In fact, I was going down the memory lane because I have worked with all of them, and this program is being conducted jointly by R.C. Thiruvananthapuram and the National Center for Innovations, with which also I was very, very intimately connected. While listening to the Honorable Speaker, my compliments to him, because I feel that he is an excellent teacher. He was reminding me of the famous book by George Gamow, 30 Years That Shook Physics, and that is where it makes references to the iconoclasts of modern physics, relativity and quantum mechanics. And today we are exactly 100 years ahead of that, and I think we are going to see another revolution. The Honorable Speaker has exposed us to so many ideas, the way he, without mentioning, exposed us to the idea of Schrödinger's cat, or the uncertainty principle, by saying how the system gets disturbed by going to observe it. It was excellent, sir. And,
Thank you.
I have enjoyed it. I've enjoyed it thoroughly. I was just many things have come to my mind. Just one or two of them are just like this: that how is India doing in the field of supercomputers? I think, without being complacent, that we did quite good in supply chain management during the COVID period. That was one of the questions. And your encryption, this RSA algorithm, in fact, that appeared to be a little bit, what should I say,
Over the top.
well, a little bit dreadful, but the very idea of starting with a semi-prime
Right.
and sort of challenging the Euclidean algorithm. But which are the good texts to go about with that? And how, as you had mentioned at some point of your lecture, that it is we who falter by not creating good passwords. So I got really worried. Means what is really the message you want to convey through this? Maybe I have not been able to organize my question properly.
No, I got the idea. Yeah. So,
but
so the first,
once again, tremendous compliments to you for an excellent deliberation.
thank you, Dr. Ghosh. Yes, I appreciate that. Let me answer that quickly. So the first part about how is India doing? Unfortunately, that has not been our priority, until recently. And so, it's never late when you wake up, and you can. That whole idea should start in people's mind that we can do this. We should be able to do this. And I think now that the government has put some actual, resources into it, it's a very commendable job. It's not an easy thing. 76,000 crore rupees they announced a couple of years back, and now they are putting more money into this, 100,000 crore rupees into this. It's a big investment for in a country which is still developing. I would say that there is also a shortage of expertise in certain areas. And expertise, I mean, not just in terms of people being able to, people are educated. They are educated, but not in the area where we need them to be educated. And educated in the way we need to be educated, meaning to have this concept of we need to invent something. It's not about we need to read what people have done, but we need to invent something of our own. And it's not that complex. We know what the problems are. So what are we doing? And are we really spending day and night doing all of that? I mean, any country which is doing this is not because they are gods or anything. It's just because they put their resources and they really spend enormous amount of time talking to each other, discussing this and doing all of that. So anyway, so that's one aspect of this. As far as this password and encryption is concerned, it has been an issue, by the way. The U.S. government has taken big notice on this, and all over the world, I'm sure governments are worried that it is coming. Decryption of your encrypted password is coming. It doesn't matter what password you use. If a good quality supercomputer, quantum computer comes, you will be in trouble. So you better start worrying about the quantum safe encryption. In fact, some of the companies and some of the banks, for example, in the US and other places in the world, I think they've already started thinking about how to have quantum safe, encryptions in their password protection and all that, the privacy protection stuff. But I would say if you want to read that, I think any search for Peter Shore and look at his work, you will enjoy the basic knowledge behind what goes on. But a good password will be something which will be long. These days, it's much easier to have a password. Make a password which is a sentence instead of a word. A sentence is like a exponentially much more complex to break than a word is. Words are easy to break because most people are very naive. They will have their password as somebody's birthday, somebody's name, boyfriend name, girlfriend name, wife's name, children's name, anything like, some date of birth, because people just want their life to be simple. But then how about that? Instead of that, how about writing a sentence instead of a word? That becomes much more complex to decrypt. For example, for a layman. So I would just use that. I think most of the places do allow, most of these workplaces, obviously they allow, in fact, we are forced to have a sentence, not a word anymore in our work culture, but many places, that's what people should be using. And use, something which is not a word, which something cannot be done in a dictionary. Otherwise, people, these days, laptops have become so powerful, they can quickly run different options and they can figure out what your password is in pretty short time. So we don't want to go through that part. Anyway, any next question, please? Okay.
Yes, sir. Good evening, sir.
Good evening.
Yes, sir. Sir, I want to ask regarding this uh, quantum computing. What are the challenges and what are the opportunities in this quantum computing?
So as I mentioned earlier, the challenges today are a lot. The biggest challenge is to actually build a working quantum computer which is meaningful. Meaningful means it can be used commercially, for example. Okay, we are at a very early stage. We are like an infant stage of a quantum computing. We still have some computer. By the way, IBM has a quantum computers which is used by banks. I mean, commercial banks like the Chase Bank, one of the world's largest banks. It uses IBM's quantum computers. We have quantum computers being used by Cleveland Clinic Foundation. It's one of the best hospitals in the world. So we have them, but that's mostly at the research level. It's not being done at a commercial level right now. And as I mentioned, the reason being decoherence time is one of the biggest drawback. That think of a computer which shuts down in less than a second. Okay, you turn it on, it does its calculation, it's done. Okay, so that's where we are today. So we are at the very infancy of this. We are trying to find out other ways where, first of all, we can keep this computer on for a long time. So we can do lots of computations until it shuts down. Or we, at the same time, we also want to have the errors that's coming because of interaction with the environment. I told you we are working at the atomic scale, right? We're working at the atoms and electron scale, at very small scale. Then everything affects, even the light affects. If you bring any electromagnetic field around it, that affects. Even the temperature affects. Everything affects here. So we want to maybe come up with a newer idea, something else, where none of these effects are relevant. As I said, in nature, nature builds all these trees and plants and flowers and life. You know, it is not done at a 0 degree Kelvin. It's done at a room temperature. We at a normal temperature. So we need to come up, maybe think more. Maybe go out and look at how are things working at the atomic scale in nature, and see if we can learn something from here. So this is, as I said, quantum computing is where we are at the early stage. So it's open to ideas. They have given you one way of building a quantum computer, but now come up with other things. So because if you come up with other things, they already have a way, so you can combine the two, and then to do things faster. So at least what I should say, the foundation is set, and it's time to launch in different areas, different people. So as I said, many companies are trying all kinds of different techniques there. And China is quite ahead in that, because they have spent a lot and lots of money into this area, and they claim that they have a much more powerful quantum computer. I don't know how much is true, because not much of it has been published. But it's one area where we should all, and those of us who are at least in this area, interested in this field, should be, thinking more deep.
Thank you, sir.
You're welcome.
Thank
Right.
you, sir.
Thank you, sir.
Yeah, sorry. Is it audible?
You can, if no one has to ask anything else, then I just wanted to make a remark after listening to Professor Upreti. That is, these are wild ideas which came to me. I found that the string of years starting from 2020 to 2025, say there is a class of numbers which Professor Upreti would be knowing, Harshad numbers,
Yes.
which is a number which is always exactly divisible by the sum of the digits. Now all these six starting from 2020 to 2025 are Harshad numbers, with the exception of 2021. But 2021 again, which is not a Harshad number, is a semi-prime. It is 43 into 47. And if you go on slashing the digits of 2021, if you slash the first two, you are left with 021, which is 21. That is a semi-prime. If you slash 0, then you have 221, which is again a semi-prime, 13 into 17. If you slash the second two, you are left out with 201, which is again a semi-prime, 67 into 3. And if you slash the last one, you are left out with 202, which is again a semi-prime, 101 into 2. Nothing relevant to your talk, but this idea just occurred to me while listening to you, particularly about this RSA algorithm.
In fact, that's a field where if you know about the Riemann zeta function, that's a field where yeah, mathematicians have spent, God knows, hundreds of years. We still don't know an algorithm to build prime numbers. Okay,
Right.
we don't know where they come from. If anybody ever knew that, that will be the end of RSA encryption as we know today. So fortunately, nobody knows, and we hope that nobody comes to know this until a quantum computer is built, or until we have better security measures. Otherwise, it will be a chaos around the world. Everything will be visible to everyone.
And sir,
But
you know, this 2023 again, it is a Harshad where the sum of the digits is 7. You don't, from 1 to 12, we have algorithm of division by every number except 7. and
Right.
2023 is exactly divisible by 7, and the quotient taken is a perfect square, 289, which is 17 square. So
Right.
this
I know
all these
that's
things
also.
just
Yeah,
occurred
I
to me
know.
while listening to you.
But in the encryption word, the number that they talk about are numbers which are in 200 to 400 digit long numbers.
Mm-hmm.
I'm talking about number of digits. So
Right, right.
imagine a number which has that many digits in it. So that's why it becomes practically impossible to break it into primes,
Into
because
two primes.
it's a product of two primes. We don't know what are those prime numbers, and that's it.
Mm.
So that's really the key here. So, but yeah, I think that will require another discussion. So let's let's go back to other people. Somebody else has any questions?
So once again,
Yeah,
compliments
Sanjay
to you.
sir.
Thank you.
Absolutely. Yes, sir.
Sanjay sir, thanks for.
No, Mr.
Once.
Tomar, I think you wanted to
Sir,
say something.
namaskar.
Namaskar.
Sir, thank you. It was really a wonderful and also very informative and thought-provoking thing, because it's the need of the hour that we need to work on the uh, the startups and also the computing, quantum computing. Sir, my question is only very. It's a simple question, sir. Maybe I feel that it's a very easy thing also, because it is quantum computing is like technical or the mathematical and also other technical areas like computer science skills are needed. But how we are going to motivate the students side or the scholars from other areas who are studying other courses. So because it is completely computer science or the technological areas, so
Yeah.
can we mix the other programs that we are offering in IGNOU?
So, right. So there are two aspects of that. One is the building part. The building
Yes.
part obviously requires people expert in this field, right? So they need to know the basics of this technology to be able to build something or come up with some new ideas. So that's obviously a scientific enterprise. Then comes the use part of these. I described earlier, different areas where things get used, and in other fields, for example, these days a lot of talk is happening on generative AI, right? Artificial intelligence and all of that. All of these use these machines, whether it's a semiconductor or it's using the quantum computing. That's what they will be using. So the use aspect of this is everybody in this doesn't matter whether they are in technical field or not. Today everybody has a mobile, everybody has they work on social sciences, for example, right? A social scientist is working on trying to solve some, let's say, social problems, right? They need data, they need to understand what's happening in human behavior, right? So anybody who is in a different field needs to interact with these machines in certain way. They need to figure out, okay, now we are going to have this much computing power, this much facility available, whether it's available today or it's in the future. How do we leverage that? How do we make use of that information to solve our type of problems that we have, right? So, for example, from the government's point of view, government says, okay, we want to have a food delivery. We want to know whether certain programs are working or not, right? Or certain policies are working or not. They need enormous amount of data from different regions. Today they do it. Most of it is done manually and all that stuff. All of that can be done with the more powerful computing, with the AI built into that. So I would say uh, people who are not in the technical field or in the scientific field related to this area need to look at the use part of it. For example, even in science, the biologists, for example, they don't understand how the quantum computer works, but they need to know, well, say in pharmaceutical industry, they need to know how to build drugs which are more effective to treat people, say research against cancer or research against other things. They need to work in their areas, but they can utilize these machines to make use of that. So I would say, people who are in the field, they work on the building the infrastructure, building these things, and then those who are outside the field should know what's happening, what's coming, so they get ready for it. They build their foundation with this in mind, that this is what is going to be available. So let's make sure that we train our people to make use of all of that. Otherwise, what's the point building something where you don't want to make use of it? if I make a computer which is billion times faster, but if you don't have a problem to solve, that's a waste of effort, right? So you need to work on the problem side. What class of problems I would like to solve using these machines. So that's what I would say.
Thank you. Thank you, sir. Thank
You're
you.
welcome.
Yeah, yeah, yeah. Can I ask the question?
Yes, please go ahead. Yeah.
Yeah, thanks. Thanks, Sanjay sir, for the today's session. It is very informative to all of us. And I have a short query regarding the qubit, as you have mentioned in the slide. Uh, which type of logic gates may be useful in the qubit? Is it the same that we will used prior the VLSI design?
No. So I'm glad you
Can you
asked that
just
question. That is one thing I did not cover in this discussion. Quantum gates are separate.
okay?
They are different class of gates. So just like in a classical one, you have NOR gate, NAND gates, all these standard
Yeah,
logic gates. Quantum computers have their own gates. They are kind of logic gates, but not exactly. Because remember, the quantum behavior is different, right? The
yeah.
qubit,
So,
is, this behavior is not deterministic, right? So you are getting a result which is probabilistic in nature,
okay.
right?
So I just guess, are they built up from the not in the using the fuzzy gates or
No,
in
no,
the
no, no, not at all.
single?
No, not at all. No. The quantum gates are more like operations. In quantum physics, there is this concept of operations. Okay,
Yeah, yeah.
and an operation is something like you have a so let's say you want to entangle two electrons. That would be an
Okay.
operation, right? You want a superposition. That would be an operation. You want a measurement. At the end of the day, when you do all the calculations, you at the end of the day, you want to measure the results. Now remember, as I told you earlier, the moment you observe the system loses its existence thereafter, right? Because it's no longer in the state in which it was before you measured it. See, in a classical system, you have a bit. It's one or
Yeah,
zero, right? You
yeah.
measure it, you get one or a zero. You know it's one or zero. In quantum, that's not the case. The moment you measure, it settles into one of the probabilistic states. So let's say I give you an example of the cat, pretty simple example of the cat dead or
Yeah,
alive,
yeah.
right?
I've
So the
seen.
moment you open the box, you see it's either alive or dead. But before that, it could be in both the states together. How do you know that what was the state of the cat before you opened the box? It's impossible to figure out. But in a classical system, you would know that the bit was one before and after, before you observed and after you observed. There's no difference. So there's a difference in the way the gates are defined. There are gates which change the spin. They rotate. They rotate the state of a qubit. So qubits are more like I would say operation on a quantum system than a digital operation on a classical system where it's basically definitive and deterministic. So ones and zeros going either it's AND gate or a OR gate or a NOT gate. So it's a different class of gates. So, but you can do at the end of the day, you can still do computations which is similar to what you would do in classical systems in a normal electronics.
Just a observation, Sanjay, means
Yeah,
as far as this quantum computing is concerned, because
yeah,
absolute zero we cannot achieve, that is for
right,
sure.
Yeah,
right.
yeah.
So it will continue to be a probabilistic.
It is, yes, it is, yes.
So how long you think that it is going to? It will set a limit to our computing power in any case, whatever we achieve.
Well,
So
so that's the
what
thing.
is the
So
future of quantum computing in that case?
correct, but remember again, the even in the today's computers that Raghavan just mentioned, digital computers also have error correction mechanism in them. They also have errors built in, but they are much less. Okay, so it's not like the today's computers are not error prone. They are. In fact, there is error checking that goes on in our own computation systems. So quantum systems are what digital computer was in 1960 maybe, okay, or 1970. So that's where quantum systems today are. So lots of errors, lots of sources of and noise in quantum systems. But people are working on those problems, and that's how the technology really advances, right? You start with a baseline where you are, you look at what are the areas, and then people start. There is, human brain is extremely powerful. It can come up with ideas over time. Many people meet together, and you get to solve this. In the you don't have to make a perfect quantum computer for it to be useful. You have to be able to make a quantum computer which surpasses the computational power of a classical computer. That's all you really need. As I said earlier, the beauty of a quantum computer is parallelism. It can do a billion, trillion calculations simultaneously, whereas a classical computer does things sequentially. One thing at a time. It can do much faster, but sequentially only. So even though quantum computer is slower, because it is happening, together at such a large scale, that it's not going to take too long before it surpasses the power of the supercomputer. And that's when there will be a turning point. It's called quantum supremacy. That the quantum becomes more supreme compared to the classical one. Classical computers are not going anywhere. At the end of the day, all human beings will still be working with a semiconductor, with all this technology, but you will be using the power of those quantum computers to solve the most challenging of the problems which your classical computers cannot do. But yeah, I mean, it will never be error free, for example. And no system is error free, but a normal system is not error free. One of the biggest advantages of a quantum computer is you don't have to worry about power consumption. The digital computer today, the semiconductor today, is one of the biggest source of carbon pollution in the world, in the environment. Really speaking, the amount of energy these machines take today, your entire generative AI, the whole Chat GPT and all that stuff, the amount of energy these machines they consume, bitcoins, the cryptocurrency, they take huge amount of energy resources from the planet. Imagine if all of that was done only on quantum computers. Quantum computers don't use much of energy at all. Okay, they are actually cold, and they need to be at the cold temperature. It's other problem. So you need to just keep them cool, and a same quantum computer can solve. So think of it this way. Let's say in theory, if I made a quantum computer which has 6,000 qubit and at the cold temperature and has a pretty decent error rate, I can solve all the world's problems, computations, with just that one quantum computer. You don't need more than 2 computers to do that. That is not the case with classical computing, not with supercomputer. Every country needs its own supercomputer. Everybody needs their own stuff. That is where we're talking about. The scale and the enormity of the problem the quantum computer can solve is way more than what a classical computer will ever be able to do. So yeah, there are challenges, but it's a matter of time.
Thank you.
Sir.
Yes.
Actually, the question is queries based on the queries for the logics. Thanks, sir.
Absolutely.
Thanks.
We can take this question from Manoj Singh ji, or otherwise then we can conclude otherwise. Okay, Ajay.
So somebody has, I think there is a question here in the chat box. There is a question. I think somebody has said, can you discuss a role of startups in developing quantum computing?
Okay.
So
Dr.
opportunities optimized for AI and machine learning. So let me talk this way. As far as the quantum computers themselves are concerned, there are obviously opportunities. As I said, it's a very early stage of development. So everything is an opportunity here. Come up with your own quantum computers. First thing is to understand how this thing works. So all these people who are really entrepreneurs, they need to spend some time, sit with some experts in this field, and figure out like what exactly is happening here. Okay, so what is built, And then I enumerated some of the problems that we have with today's quantum computers. Try to see if you can come up with a better idea. So there is a plenty of opportunities, at least for innovators, startups in those areas. Okay, those are expert level things. Then there are enormous other opportunities at the user level thing. That imagine that, let's say those machines are built, if not by you, somebody else. Let's say those machines are built. Are you ready with the next level of what you call economic activity that will happen as a result of those machines being available? Artificial intelligence is one of the areas, because that's where things can get used. Today, there are a lot of bottlenecks in AI. Generative AI, as I told you, uses foundation models, which take months and months to create, and they take enormous amount of computing power and enormous amount of energy resources. Can you take leverage with these ones? Can you build your own models with AI, with generative AI, and your own foundation models? Today, foundation models can only be built by large companies, because it takes so much of resources. Let's assume you have a quantum computer available. Now you can build your own models much better. In fact, they are in some sense, quantum computers can do a better job in building the large language these foundation models compared to classical computers, because there is a distinction there. There is a fuzziness in that logic that you take advantage of. So there are all these opportunities that are available. I would say it's important for people to at least read through first, so at different levels. And I would say that work on all of them come together, like in different areas, not just stick in one of those. But I would say, for anyone, please, those of you who have the ability to start courses in quantum physics at every level, at right after inter is finished, people should be trained in quantum physics as much as possible. And I mean, seriously, lowest studies, 50-year-old book on quantum physics, something like that. But look at the that is happening. How does the quantum information science? That's really the crux of the whole quantum computing. Quantum information science, QIS. That many universities in the US, for example, they have courses there. I'm sure in India too, maybe a couple of universities, maybe some universities do have the courses, maybe certain in IITs, but not most of the places. Start course on quantum information science. How, teach them, get them trained with this, because this will be useful. This will become one of the most sought after, skill for people to use these things. So, we need to work on all the skill building, to provide the labor force in those areas, building those machines themselves too. So I think we have to work in all of them combined. It's not just one or the other.
Yeah.
You're welcome.
Pranam sir, pranam sir. Pranam sir, pranam to all sir, all my seniors who are with us. Most respectable Honorable Vice Chancellor sir, Pro Vice Chancellors, Registrar Administration, Finance Officer, all school heads, senior faculties, Indira Gandhi National Open Innovation Hub, and NC8. Today, international webinar on emerging development in the field of semiconductor and quantum computing opportunities for innovations and startups. To virtual mode, and especially Director NC8 and Director RSD for supporting today's event. Thank you so much for it, sir. And it has been such an honor to be a part of today's wonderful event. On behalf of Indira Gandhi National Open University, New Delhi and Region Center Trivandrum, I would like to extend my heartfelt gratitude to our esteemed guest, Sri Sanjay Upreti ji, Senior Engineer, Data Scientist, or we can say he is a scientist. Today, as a layman, we all could understand. Today, as a layman, we all could understand what is semiconductor and computing, etc. IBM Corporation from United States of America. Thank you, sir, for your interesting keynote address. And today we had an opportunity to have thoughts, and this will surely be going to encourage our young youths to build a strong nation towards Viksit Bharat. Honorable Prime Minister claimed for transforming India into a developed nations. by 2047. Thank you, sir. Thank you so much. It's
Thank you very
mind-blowing.
much. Yes.
And I thank respected Dr. Umesh Chandra Pandeyji, Regional Service Division Director, IGNOU New Delhi. Thank you, sir, for your wonderful presidential address and your beautiful question, which sir has explained very beautifully. Thank you so much. And I respect Dr. Om Prakash Sharmaji, Director, National Center for Innovation and Distance Education. Thank you, sir, for your innovation special address. And also today, through OP Sharmaji, the innovation things are developed in Trivandrum because of his support and the Honorable Vice Chancellor support and Director RSD's initiation. Thank you so much, OP Sharmaji, sir. Thank you so much. And I thank Dr. Rajesh G, Senior Regional Director, Indira Gandhi National Office Regional Trivandrum. Thank you, sir, for your welcome address, and Apollo's thanks for making the event memorable and incredible support today. And we can call you as conductivity between conductor, because sir was sitting in USA and the sir couldn't, in the starting, there was a problem. So immediately sir was transformed into the mobile as a WhatsApp message and he has presented in our screen. Really great, sir. It is an asset for IGNOU. Dr. Rajesh is there. He is the youngest regional director when he has joined it. Now he is a senior regional director. Still he is young. We need your lot of support. Thank you so much, sir. And I would like to take a moment in thanking all regional center officials who participated, LSC functionaries, coordinators, and delegates, dignitarians, participants all over India, not only in IGNOU, all over India, and prospective IGNOU students for this wonderful event. Thank you, one and all. And our Director Computer Science has also cooperated in this aspect. I thank the Director, School of Computer Science and Information Science. And I thank the technical staff, Sri Sajit, for this technically supported us for today's event, grand success. And I thank CPWD, who has provided electricity power. You know very well. RSG sir also know very well. Today we have moved to the new building. We are facing lot of problem, but beautiful and mass success was the program. Otherwise, CPWD has supported a lot. Thank you, one and all. Thank you, one and all. Thank you, sir. Pranam, sir. Pranam.
Thank you.
Thank you, Sanjay. Okay. Okay, Rajesh.
Thank you, Dr. Rajesh. It was very good to see you. Thank you, everyone. I appreciate the time.
Thank you, sir.
Thanks, Sanjay sir. Thanks, all the team members.
Thank you. So we
Thank
can
you,
stop
sir.
it here now.
All team members, thank you. Thank you.
Thanks to all, sir.
Thank you so much, sir.
So, Dr. Rajesh, do you want me to send you those couple of videos which I think people should watch because it's important for the manufacturing process, how that happens? I'll send it to you separately. Yeah. Okay.